I was just reminding you that benzene with NH2 is aniline. By the way, these could also be carbon chains, and this would still be electron donating. So it's, these could be carbon chains here as well. This could be, say, NHR or NR2, and it would still have the same properties. It would still be an amine group, so you could expect it to have the same properties. Whoops. Electron donating or withdrawing?
Donating.
Through?
Resonance.
Yeah, again, there's a lone pair. Through induction, this would again be electron withdrawing, but the resonance is more important. Incidentally, you should know the common name for this compound.
Phenol.
Phenol, good. That's a very logical name, isn't it, phenol? Because phen indicates the phenyl, the benzene ring, and OL indicates the alcohol. So this is a benzene alcohol.
They also called it benzenol.
That's right, it could also be called benzenol. However, it's much more common. So the official IUPAC name is benzenol, but actually in real life, everyone almost always calls it phenol. And again, this could have been an OR instead. Instead of an OH, it could be an OR. That wouldn't be phenol anymore, but it would still be electron donating through resonance. All right. Now, the halogens, so we've basically gone over all the substituents that you could kind of figure out on your own steam. So here's the substituents that are electron donating and activating. These are electron donating through resonance. Alkyl groups are electron donating through hyperconjugation. Here's the electron, and here's the substituents that are electron withdrawing and deactivating. CF3 is electron withdrawing by induction, and these other ones are electron withdrawing by both induction and resonance. Now the halogens just have to be learned separately. The halogens are basically their own category. The halogens have two conflicting effects. They have electron donating by resonance, and they're electron withdrawing by induction. However, now for one thing, we're usually not going to talk too much about fluorine. Fluorine doesn't come up too much in OChem. So if we're talking about the other halogens, the big difference is that they're much bigger than the carbon. And we talked about this briefly before. Remember that resonance occurs by side-to-side overlap of p orbitals.
And that when the Cl's p orbitals are much bigger than this carbon's p orbitals, so they can't overlap well.
That's right, they don't overlap well. That means although this can donate electrons by resonance, it's going to be ineffective at doing it. So the resonance effect here is weaker than it would normally be. The resonance effect here is weaker than it would normally be. So overall, these are electron withdrawing. Overall, these really are electron withdrawing. This is one case where the induction effect kind of wins out over the resonance effect. But because it's such a close call, these really should be thought of as a separate category that we'll just have to memorize. We're basically, instead of understanding the halogens, we're just going to have to memorize how they behave, because there's a close call between the resonance and the induction. But again, because chlorine and bromine are bigger than carbon, their p orbitals are much bigger than the carbon's p orbitals, so they're not very effective at resonance stabilization. So there's a close call between the induction and the resonance. So here I'll put the halogens. X for halogens. We'll use X for halogens here. So the halogens, so this line here is the separation between the activators and the deactivators. If it was just a hydrogen in this position, that would be neutral, so to speak, right? If this was just a hydrogen, that would be neutral. So everything above the hydrogen is more electron donating than hydrogen, and everything below the hydrogen is less electron donating than hydrogen. Notice that I put the X here very close to the line, though, to show that it's only slightly electron withdrawing. It's not as electron withdrawing as these other substituents down here. Incidentally, I think nitro is just about the most electron withdrawing, so I put it at the bottom because it has that full positive charge on the nitrogen. And again, these groups are more electron donating than alkyl groups because they have resonance in the alkyl groups.
What is the most donating?
I suppose it would be
the OH?
The OR.
I suppose it would be the nitrogen because since it's the least electronegative, it's the most willing to donate its electrons. Remember that if you compare elements in the same row, you should focus on their electronegativity. Well, since the nitrogen is less electronegative, it's more willing to give up its electrons. So I would guess that this is the most. But the most important thing is just to know that these are more electron donating than an alkyl group. This is electron withdrawing, but not as much as these. And the nitro is the most electron withdrawing. That's about as much detail as you probably would be expected to have. But it might be good to have this kind of table in your notes here, the way I have it arranged. So let's imagine that we've already attached a chlorine to the benzene ring. If we've already attached a chlorine, now we're going to try to do a Friedel-Crafts alkylation and add this carbon chain. Is it going to be easy or hard to add this carbon chain?
Hard.
Because
The Cl is, I don't know why we had learned it that it was withdrawing, but because it's withdrawing.
it is withdrawing.
Yeah, we had learned it that it was donating for some reason.
The halogens?
That it was donating, but it was still deactivating.
All right. Is that what your professor said?
I think our GSI said that.
Okay. Well, I have more courage to disagree with your GSI than your professor. This is a little bit delicate because the halogens are really a special case. I think the best way to describe it is that the halogens are slightly electron withdrawing, and that's the reason that they're deactivating. But there are some subtleties that we'll be getting into later.
Okay.
So maybe the best thing is just to remember not to even worry about the electron donating and withdrawing. Don't even worry about the electron donating and withdrawing. Let's just memorize these are slightly deactivating. Because these are a special case, maybe we should just memorize that halogens are deactivators. And we won't worry about the electron donating and withdrawing, because that's more subtle than we really need to get into. We'll just memorize these. The other groups we were able to explain, but the halogens we won't try to explain too much. We'll just memorize that they're slightly deactivating. So what did we decide? Is it going to be easy or hard now to add this second substituent?
Hard.
Hard. Because the chlorine, is this an activator or a deactivator?
Deactivator.
Why? Because we just memorized that halogens are deactivators. We're not going to try to explain that too vigorously in terms of electron withdrawing and donating. Now, let me point out the mistake that I see students make here a lot. Here's the mistake. Is this an activator or a deactivator?
Neither. It's not on a benzene ring.
That's true. But once it's on the benzene ring,
Oh.
Activator.
right, well, it looks like you're definitely not going to fall into the trap. But the trap is, a lot of people ask whether the next substituent is an activator or a deactivator. And then they would say, oh, this is an activator, so it should be easy to add it. But that's a big mistake. You guys are avoiding that mistake. What matters is the substituent that's already on the benzene, not the new substituent you're trying to add. Maybe I shouldn't have brought this up since you weren't making that mistake anyway, but I do see people end up making that mistake. So like when I asked you whether this was an activator or a deactivator, you said, who cares? Well, that was really the right answer. We shouldn't even be wondering whether this is an activator or a deactivator because it's not on the benzene ring yet. What matters is the substituent that's already on the benzene ring. So maybe I shouldn't even have labeled this in the first place. Okay, so when we're deciding whether this reaction will be hard or easy, should we focus on the substituent that's already on the ring or the substituent that's moving onto the ring? We should focus on the substituent that's already on the ring. And we shouldn't even bother worrying whether this new substituent is an activator or a deactivator. This is only going to have an effect maybe if we try to add a third substituent. If we try to add a third substituent, well then this would have an effect because then it would be on the benzene ring. But it has no effect on whether it's easy or hard to add itself. What matters is what's already on the ring. Okay. So you guys gave the right analysis. This is a deactivator, which is going to make it hard, but probably not impossible because these are only slight deactivators. Incidentally, if you have a really good activator on the ring, you might not need a catalyst anymore. Remember that we saw that when you add the first substituent, we need all those Lewis acid catalysts. But if you already have a really good activator on the ring, you might be able to get the reaction to go without a catalyst. Sometimes students get confused by that because they'll see a reaction in the book without the catalyst and they don't know why they're doing that. That's because there's already a strong activator on the ring. If we say put this on the ring first, we probably wouldn't need a catalyst to say to add a halogen then.
Okay, but if you added the catalyst, would it be wrong?
No, I don't think so.